Okay, in this video, I want to give as brief of a overview as I possibly can about calculating residues. And I want to do so using some really common residue calculating techniques. Remember that a residue is the B1 term where you have the Laurent expansion. So you have a BK over Z minus Z naught to the K, all the way down to B1 over Z minus Z naught, plus some analytic function, which I'll just continue to call lambda. And so this B1 term is the residue. That's what we're after. Of course, if you can actually calculate the Laurent expansion at a point Z naught, then you have the residue right there. Okay, but in general, calculating the residue is easier than finding the entire Laurent expansion. So you're doing too much work if you're trying to find the Laurent expansion. So I want to concentrate just on how you can find that residue there. And the first case is when you have a holomorphic function or even a removable singularity. What's going to happen there? So if f is holomorphic or has a removable singularity, what's going to happen is that your function is just going to be this analytic part. It's just going to be this lambda. So it's going to be this a0 plus a1 z minus z naught plus a2 z minus z naught squared, and so on. And therefore, your residue is 0. There is no z minus z naught to the -1 term. But anyway, so your residue is 0. So not much more to say there. That's good to remember, though, in general. If you have a holomorphic function of removable singularity at z naught, then the residue is 0. And that's the end of the story. Part 2 says the following. So if you take z minus z naught and you multiply that by f, and if this limit exists but is non-zero, so if this is equal to L and L is not equal to 0, then this value L is the residue. And so just think about what this means. If z minus z naught is going to exist but not equal to 0, then this tells you two things. This tells you that you can't, so basically what this forces, I'm being a little hand wavy here, but there's no other scenario where this works except where you take a function that looks like b1 over z minus z naught plus a0 plus a1 times z minus z naught, and so on. The function f has to look like that. And therefore, when you multiply by z minus z naught, what's going to happen is, so if you look at z minus z naught times f, this is going to be b1 plus a0 times z minus z naught plus all the higher powers. And when you take the limit, if this limit exists but does not equal to 0, what you're going to get is this term b1. So whatever this limit is, that's the residue. Okay, that's basically how this works. And then you have to convince yourself that all the functions such that this limit exists but does not equal to L must look like exist but is not equal to 0. I mean, all those functions must be functions with simple poles, because if you had higher powers in the denominator, then when you multiplied by z minus z naught to the first, you wouldn't have a limit that exists. It would go to infinity. And if you had no term here, if you had just the analytic part, then when you multiply by z minus z naught and you take the limit as z approaches z naught, you would get 0. So the only case that works here is when f has the simple pole, and therefore the residue is going to be this limit. Okay. The third case, and I'm going to talk about just a few kind of special cases here, but if you have a function f that's g over z minus z naught squared, where g of z naught is not equal to 0, this is going to be a double pole. So this is a pole of order 2. That's what I mean when I say double pole. So this is going to be a pole of order 2. And the way that this is going to work is that you can calculate the residue of f at z naught by just calculating the derivative of g at z naught. And I'll explain this formula in a second. This is actually more reasonable than I write. One other scenario, and then we'll talk about this in general. If you have a function that's g over h, and if g of z naught is non-zero, h of z naught is 0, and h prime of z naught is non-zero, what this means is that, think about this just in terms of Calc 1. If you have a function that when you plug in a point you get 0, that means you can factor out a z minus z naught from that function. And when you take its derivative, if you don't get 0, then you could only factor out z minus z naught once. And so if you could take, I'm saying a little bit more here than I intended, but if you were to take a function, and if you were to factor out z minus z naught, say, cubed, then the first, second, and third derivatives would all have to be 0 when you plug in z naught, because you're going to have, from the product rule, some derivative here times this function, and you're going to have to take at least 3 derivatives until you'll get something that'll stick around, because you're going to have this to the third power in the original function. You're going to have this to the third power and to the second power in the derivative. When you take the second derivative, you'll have this all the way down to a linear term, and it's not until you take the third derivative that you'll actually get a constant times g in your derivative. So just from the basic product rule. So when you see, this is all just a way of saying that when you see that h of z naught is 0, but h prime is not, that means that z naught is a 0 of h of order 1, meaning that you can factor out a z minus z naught term from h, and then what you're left with is non-zero at z naught. So that's the scenario that we're in here. In other words, this is a simple pole. Since you can factor out a z minus z naught from the denominator, and g of z naught's non-zero, so you can't factor a z minus z naught out of the numerator and leave a nice function. So this is just a simple pole. And what's going to happen here is that our formula for computing the residues, our residue of f at z naught, is just going to be, so it's just going to be g of z naught. So it's going to be g of z naught over h prime of z naught. Yeah. These are formulas that I don't have memorized, so I am looking at my notes here. But there's a reason I don't have them memorized. And the reason why is that number 5 is kind of the one rule that kind of encapsulates everything. If, this is going to be a little bit longer to go, but this is kind of just one nice rule that works a lot of the time. If k is the smallest integer, so if k is the smallest integer, so that the limit as z approaches z naught of z minus z naught to the k times f of z exists, but is non-zero, then the formula for computing the residue of f at z naught, what this means, by the way, is that f has a pole of order k, and therefore the residue of f at z naught is going to be the limit as z approaches z naught of the k minus first derivative of phi all over k factorial. Okay, and so it's that limit as z approaches z naught. And this is kind of one rule that encapsulates almost everything that we've done so far. Here I forgot to say where phi, so phi of z is z minus z naught to the k times f. Okay, and so let's just think about why this works, and then let's think about how it implies everything else that we've talked about so far in this video. If k is the smallest integer with the property that this limit exists and is non-zero, what that means is that f has to be a function of the following form. It's got to be b sub k over z minus z naught to the k plus b1 over z minus z naught plus an analytic function. And here, b sub k is non-zero. Okay, I know it's non-zero because we assumed that in the hypothesis, right? And the place where we assumed it is that we assume that this limit is non-zero. So if you multiply both sides of this equation down here by z minus z naught to the k, you end up with b sub k, and therefore by assumption that's going to be non-zero. So this really is when you have a function that has a pole of order k. And the reason why the residue has this formula is just think about how you can find the term b1. So what we're going to do is we're going to look at the quantity phi, and that's z minus z naught times f. And if I just multiply everything in our expansion here, if our series for f, if I multiply everything, we end up with, I'm sorry, this is z minus z naught to the k. If we multiply everything by z minus z naught to the k, we end up with bk plus b sub k minus 1 times z minus z naught to the first plus b sub k minus 2, z minus z naught to the second, all the way up to, let's see, our last term that's going to be interesting here is b1 times z minus z naught to the k minus 1, because we're multiplying both sides by z minus z naught to the k, plus z minus z naught to the k times our analytic function lambda. And if you think about this, and if you look at this for just a second, you'll realize phi is actually going to be, it'll have a removable singularity. It's analytic at z naught, because you can write it as a power series. Here's your constant term, your linear term, your quadratic term, and so on. Okay, and you get all the powers of k that you want. So phi is going to have a Taylor expansion, and therefore we have a formula for what the coefficients are. And in particular, if we're looking for the coefficient of the k minus first term, then b1, which is nothing more than the residue of f at z naught, is going to end up being the k minus first derivative, because it's the k minus first power, divided by k factorial. And I add in this limit as z approaches z naught, because this is technically a removable discontinuity. We have to kind of take these limits just to make sure that everything works out nicely. But this formula comes exactly from Taylor's theorem. And moreover, the reason why this is the best of all the 5 methods that we talked about, well, at least of the last 4 that we talked about, is that it encapsulates all of those. And so let me just very quickly, as I can, show you how all the other rules follow from number 5. So for example, the rule number 2 that we just talked about was when k is equal to 1. And so if k is equal to 1, there's really nothing to do. If k is equal to 1, you're going to take the limit as z approaches z naught, z minus z naught times f is going to be L, that's non-zero. That's literally the case when k is 1. And so then the residue is going to be this function, phi. So it's going to be the limit of phi over 0 factorial as z approaches z naught. And that's just literally this limit L, because this limit, I mean, phi is exactly z minus z naught times f of z. 0 factorial is 1. Everything's fine. So this limit is really L. So number 2 follows from this rule. Number 3 follows from this rule, because number 3 said that if you have a function f that's g of z over z minus z naught squared, and g does not have a 0 at z naught, then it turns out that this will be a pole of order 2, and therefore your phi is going to be z minus z naught squared times f, and that's really just g. And so what you're going to do is, if you have a pole of order 2, then your k is 2, and therefore your residue, so the residue of f at z naught is going to be the limit as z approaches z naught of the derivative phi prime, which is really just g prime of z, as z approaches z naught, and that's really, of course, just g prime of z naught. Okay, so even that follows from number 5. Number 4 also follows from number 5, although I'm not going to, number 4 is fine. There's one that I'm not going to walk through the calculation, and that's when you have a double pole. So when you have f is g over h, the calculation really only works in this case when you have a pole of order 1. So here we're assuming that g of z naught is non-zero, h of z naught is 0, h prime of z naught is non-zero. And in this case, what's going to happen is you're going to have a pole of order 1, because if the first derivative is non-zero, but the original function is 0, that tells you that you have a 0 of order 1. So you can factor out a z minus z naught, and then everything else is nice at z naught. And therefore, what you can do is you can look at phi, and phi is going to be z minus z naught times f. And when we take the limit of phi, this is going to be the limit. So if k is 1, this is just going to be the limit of the 0th derivative, because you take k minus 1 derivatives. Our k is 1, so you take 0 derivatives. This is going to be the limit of phi as z approaches z naught. So that's going to be the residue of f at z naught. And what's phi? Well, that's z minus z naught times f, where f is g over h. So we take the limit as z approaches z naught. And then notice that what's going to happen is you have 0 over 0, and you apply L'Hopital's rule. And so this is going to be the limit as z approaches z naught of, let's see, the derivative of the top is going to be g plus z minus z naught times g prime, all over the derivative of the bottom, which would be h prime. And now when you take the limit as z approaches z naught, this term will go away. You end up with g of z naught over h prime of z naught. Okay, and that's how rule 4 follows from rule 5. So really rule 5 is the only thing that you need to know of all the methods that we've talked about in this video to find the residue. Okay, and so this works basically in most of the times that we're going to talk about. Again, the only times when it really doesn't work is when you have an essential singularity, and when you have so when you have an essential singularity, there's really nothing you can do other than just to find out what's the actual Laurent expansion. That's the easiest way to compute the residue. So if you were to have something like sine of 1 over z or e to the 1 over z, you need to know the Taylor series for e to the t, and then plug in 1 over z, and then you get the Laurent expansion, and then you can calculate the residue, and life is grand there. But anyway, so this is a rule that I think is very useful. This rule number 5 is useful in calculating residues. Okay, so in the next video, we'll talk about some examples of actually calculating residues.